In the last video, we saw three laws known as Boyle's Law, Charles' Law, and Gay-Lussac's Law. And we combined them at the very end into a single relation, that is that the pressure times the volume is proportional to the temperature. In this video, we're going to finish up the equation and put it all together. So to finish up the equation, we consider another relationship. Here in this figure, you've got a little boy who's blowing up a balloon. Is he changing the pressure? No. Is he changing the temperature? Well, excuse me, he is changing the pressure, yes. But that's not a huge issue because as the pressure increases, the balloon expands and the pressure goes back to normal. But he's not changing the temperature much. Really, what's changing the volume inside of the balloon is the mass. So the volume of a gas is also proportional to the mass of that gas. So let's talk a little bit about the mass of gases. Molecular mass of a substance is going to equal the total mass of each atom within the molecule. If you look at any periodic table, you can find the atomic mass there. You have small numbers. For instance, you can't see it here. Oh, you'll see this in just a second. I'm going to zoom in. But you have a small number, like by the H, there's a 1. And by the hydrogen, helium, there's a 2. That's the atomic number. Talks about how many protons are in an atom. But underneath there is a decimal number. For hydrogen, it's 1.00 something or other. But for helium, it's 4. Those numbers are the atomic mass. They talk about the total mass of the nucleus of that atom, protons plus neutrons. So for example, what's the molecular mass of carbon dioxide? Well, carbon and oxygen are right here, so we're going to zoom in on that. All right. So if you look, carbon has a mass of 12.0106. That's the carbon. But we also need to add in the oxygen, which is down here at 15.9994. But we have 2 oxygen atoms. And so we have to take that number and multiply it by 2. Because since there are 2, we have to add both of their masses. So the total molecular mass then, I'm going to pull out my calculator here so I can calculate it for you, would be 12.0106 plus 2 times 15.9994. It gives us a total molecular mass of 44.0094. Well, what are the units? Well, we'll define it here as something called grams per mole. Now, a mole is defined as the number of grams of a substance that is numerically equal to the molecular mass of a substance. In other words, 1 mole of carbon dioxide is going to have a mass of 44.0094 grams. That's the idea of a mole. It's the number of grams of a substance that's numerically equal to the molecular mass. So hydrogen, which has a molecular mass of 1, hydrogen gas is H2, therefore 1 mole of hydrogen gas is equal to 2 grams. Neon, if you go back and look at a periodic table, you can't see it here, but neon has an atomic mass of 20. So 20 grams of neon would be 1 mole of neon. And then, just like we just calculated, 1 mole of carbon dioxide has a mass of 44 grams. And so your molecular mass that we just defined as having units of grams per mole, if we take the total mass of a gas, whatever the amount is, divide that by the molecular mass, then we get the number of moles we have in the substance. And we use this N, which is the number of moles of a substance, in our ideal gas equations. The full ideal gas law would then be pressure times volume is equal to the number of moles times R, which is a constant number, times the temperature. And once again, I have to stress that the number of moles is related to mass. All right, so N is the number of moles, R is the universal gas constant, and the value of this constant depends on the units you use. Standard units that we use here in this class would use joules, and so the number would be 8.314 joules per mole Kelvin. Likely you learned the second number in your chemistry class if you took one already. That number is 0.0821, and the units would be liters times atmospheres per mole Kelvin. Now, if you go through and do a unit analysis and convert units back to cubic meters times pascals, which would equal a joule, you would see that that unit conversion will get you back to 8.314. Another unit for energy is the calorie, which we'll discuss more in chapter 14. But a calorie, using the unit of calories for energy, the R constant would be 1.99 calories per mole Kelvin. Okay, that is the ideal gas law written in terms of the number of moles of a substance. But a scientist by the name of Avogadro determined how many molecules was in 1 mole of a gas. And that number is 6.02 times 10 to the 23rd molecules per mole. You don't really need these units, but I'll write them in anyway, just to clarify that 1 mole of a substance has 6.02 times 10 to the 23rd molecules. And so if you want to know the number of molecules in a gas, any volume, any number of moles, whatever, the number of molecules you have would be the number of moles times Avogadro's number. And we can also solve for the number of moles in a substance. That would be the number of molecules divided by Avogadro's number. And we can use this in our ideal gas law equation. We have PV equals nRT. But N, we just barely saw, lowercase n, the number of moles, is going to equal the number of molecules divided by Avogadro's number, which, just rearranging the equation a little bit, the R and Avogadro's number are both just constants, so we can combine those into one constant. If we take R, which is 8.314 joules per mole Kelvin, and divide that by Avogadro's number, 23rd molecules per mole. The moles cancel out, and your number comes out to be, oh, it's right here. Your number comes out to be 1.38 times 10 to the minus 23rd joules per Kelvin. And that is another very common constant that's used in the ideal gas law in this form, where instead of using the number of moles, we use the number of molecules. And K, which is this value of 1.38 times 10 to the minus 23rd joules per Kelvin, is known as the Boltzmann constant.